So in the text, section 4.7, numbers 344 to 347. So section 4.7, 344 to 347. Yeah, I use OBS Studios for recording. Because all the hip Twitch users use OBS Studios, right? Any of you guys Twitch streamers or something like that? That's actually not the reason I use it. But just, just to put an air of mystery around it. So numbers 344 through 347. So this was also question, the last one on exam 2. So where is that? So number 6. Number 6 on exam 2. So finding the absolute max and min for a continuous function on a bounded interval. Not continuous, we'll say differentiable function. So smooth and continuous. So always has derivatives, smooth and continuous. So this is what this topic is about, and it didn't really seem to get like folks really sort of understanding this. Okay, for a single variable function, how is this done? So for a single variable function, we're not in a bounded interval, in a bounded domain. For a single variable function, y equals f of x on the interval a less than or equal to x less than or equal to b. How is this done? How do you find the absolute max and min? So this is from Calc 1. How do you?
You have to take the derivative, set that equal to 0,
right,
and then plug in that x point and then the end points.
Right. So step 1, find f prime solutions to f prime of x equal to 0. Say points C1, C2 through Cm or something like that. Find the solutions to that. Maybe we'll call them x. x1, x2 to xm. 2, compare f of a, the endpoint, f of x1, f of x2, f of xm, and f of b. So test f on the endpoints and the critical points. All right, these are called critical points. Right, and then compare f on the critical points and on the endpoints. So compare these, pick the largest and smallest values. among them. Right? In other words, right, the max min values of f of x occur at critical points and at and or at the endpoints. So for a single variable function, that's what you get. Okay, the max and min values are at critical points or at the endpoints. What are the critical points? The solutions to f prime of x equal to 0. Okay. For a two-variable function, so for a two-variable function or more, 3-variable, 4-variable, 5-variable, z equal to fxy on bounded domain. So here the domain doesn't have to just be an interval anymore. I mean, it's, you know, it's some potato-shaped thing, right? On some bounded domain D, okay, the max min values, it's the same thing as the single variable case. Same thing as the single variable case. The max min values of f, x, y occur at critical points and or on the boundary of D. Occur at either critical points inside D or on the boundary of D and or. Okay, so step one, right, solve, so find all solutions to fx equal to 0, partial derivative of f with respect to x equal to 0, and partial derivative of f with respect to y equal to 0. Find all solutions to this pair of equations. No longer a single equation, pairs of equations. Find all solutions to that. These are your critical points. 2, on the boundary of D, the two-variable function fxy becomes a one-variable function. On the boundary, the two-variable function becomes a one-variable function. Why? Because the one-variable function can be, because the boundary can be described as a curve of one variable. Okay? Well, if you can do it that way, which, you know, in all the problems I ask, you can. So on the boundary of D, the two-variable function becomes a one-variable function. Find the max min values of the single variable function and then 3, compare fxy at critical points and max min on the boundary. Pick out the largest and smallest values. And that's the answer to your problem. So it's the same with the two variable function. It's the same as the single variable function. It's just got a little, couple extra steps. You have to find the critical points, then you got to look at the boundary. With the single variable function, you find the critical points, and then you look at the boundary. So let's take a look at exam 2. Where'd it go? So on exam 2, it looks like I don't have the actual problem. Where is it? Let me actually find it. And we'll do that.
For these kinds of maximum minimum problems, could we parameterize the boundaries instead of just leaving them in terms of x and y?
That's essentially what you'll be doing, yeah. It becomes a single variable. So you will eliminate x by writing it in terms of y, or eliminate y by writing it in terms of x, or eliminate both by writing them in terms of t, something like that. Okay, the two variable function will become a one variable function, either just x, just y, or some new thing, t. Okay, here it is. So find the absolute max min of fxy is 2x squared plus y squared. All right, so this is exam 2. So we'll find the max min value of fxy equal to x squared plus 2y squared. Right? Is that what it was? Or 2x squared plus y squared. On the disk x squared plus y minus 1 squared less than or equal to 4. So what is that disk? That's the disk of radius 2 centered where? At 0, 1. Right? So here's 0, 1 in the center here. So 1, 0, -1, 2, 3 on the y-axis, and here's the x-axis. Okay, I don't know at these points, and it's maybe not important. So we're on this D here. So this is D. All right, so first find critical points. All right, so partial derivative of f with respect to x is just 4x. Set that equal to 0. Partial derivative of f with respect to y is just 2y, and set that equal to 0. So x, y equal to 0, 0 is the only critical point. Right? That's the only critical point. So let's just check out the value of that. So f of 0, 0, therefore, is just 0. All right? Now let's look at the boundary. What is the boundary given by? What is the description of the boundary of this disk? What is the description of the boundary of this disk?
The equation for the circle.
This?
It would be the equation for the circle, but just equal to 4 rather
Equal to
than
4, right, yes.
less than or
Yeah,
equal to
4. Less than or equal to 4 give you the inside and the boundary, right? So the boundary is x squared plus y minus 1 squared equals 4. So So that is the circle itself, not the inside of the circle. When you say less than or equal to 4, it gives you the inside of the circle. Okay, fine. So here, x squared is 4 minus y minus 1 squared. Right, so fxy, which is 2x squared plus y squared, becomes, on the boundary, so normally you would solve for x. So like x is therefore equal to the square root of 4 minus y minus 1 squared. You know, and then plug that x into here. But we don't have to do that. There's no x's here. There's just x squareds. There's just x squared. So figuring out what x squared is supposed to be is good enough in this case. So here, this reduces to the one variable function, f. I'll just call it f. Or you can call it a new thing, g of y or something. X squared is this. So it's 2 times 4 minus y minus 1 squared plus y squared, right? X squared becomes this. And so that gets plugged into here. What is the range, what is the domain for y in this case? Look at that picture. Look at that picture. What's the values for y that we're working with here?
-1 to 3.
-1 to 3. Right, so minus 1 less than or equal to y less than or equal to 3 by the picture above. All right, so let's simplify this. It's just a quadratic polynomial. So g of y is just equal to 8 minus 2 times y squared minus 2y plus 1 plus y squared. So g of y is equal to, so I have y squared minus 2y squared. So that's minus y squared. And plus 4y minus 2 plus 8 plus 6. Right? 4 minus 1 less than or equal to y less than or equal to 3. So that's a single variable function on a bounded interval. So how do we find the max min value there? How does that work again for the single variable function?
Take the derivative of g of y and evaluate its maxima, minima, and critical points. Or
Yeah.
evaluate its boundaries and its critical points.
Yeah, and that point there. So you take the derivative, g prime. So we got minus 2y plus 4. Set that equal to 0. So that gives me y equals 2. So I've got one critical point and then the endpoints. Right, so I have y equal to minus 1, 2, and 3. So that's y, and then this is g of y. So at minus 1, what do you get? Minus 1, minus 4, plus 6. So that's 1. And then at 2, what do you get? You have minus 4 plus 8 plus 6. So that's 14 minus 4 is 10. Plus 8 plus 6. Okay. And then at 3, what do you have? You have, oh yeah, this is right. So minus 9 plus 12 plus 6, that's 18 minus 9 is 9. Right, so on the boundary, right, the max and min values are 10 and 1. And on the interior, your value at your critical point is just 0. So the max value for f is 0. Or sorry, min value for f is 0, and the max value for f is 10. So max value for fxy and min value for fxy is 0. All right, you just compare the max and mins on the boundary with the values on the critical point and, you know, pick out the biggest and the smallest. So we got 0 and 10. So let's look at another problem in the text. So this one is kind of similar to that 347. It's on a disk. fxy is minus 2y over x squared plus y squared plus 1 on the disk of radius 2 centered at the origin here. Let's not do that one. How about, this is another one on the disk. Okay, 344 looks like a good one to consider. So we've got fxy is xy minus x minus 3y. Oops. xy minus x minus 3y, and R is the region, so 5 on the x-axis, 4 on the y-axis. So we've got this triangle, so that's 5, 0, 0, 4, and so we've got this region inside here. So find the max min value, and this is 0, 0, of fxy on D. So first we check the inside and find those critical points on the inside. So partial derivative of f with respect to x is equal to y minus 1. Set that equal to 0. Partial derivative of f with respect to y is equal to x minus 3. Set that equal to 0. So your only critical point then is 3, 1. It's the only critical point. So check f at that value since we know the critical point. And what do we have? We have 3 minus 1, no, 3 minus 3. 3 times 1 is 3, minus 3, minus 3 is minus 3. Okay, so at the one critical point, and oh, let's check, make sure that's actually in the interior. So 3, 1. So where is that point actually? So it's like here, this is at 3, and then what's this point right here? So I think it's there. We're going to need to find the equation of this line right here. So this line right here, what's it going to be? So this is y is equal to, and what's the slope? Rise is minus 4 over the run, which is 5, x plus 4. So at 3, it's minus 12 over 5 plus 20 over 5. So it's 8 over 5. So this is 8 over 5. So the critical point is right there. Right, so that critical point is inside. There is a possibility that that critical point that you find, it might not actually be in the domain. It should be clear whether it is or isn't usually, but here it actually is, you know, it requires a bit of investigation. So anyway, so the value of f at that critical point is 3. So now we have to look at the boundary. Now, unfortunately with this problem, the boundary is not a circle. It's not like one continuous curve. Here, the boundary is 3 lines. essentially. So you have to look at each line separately. All right? So, boundary. So let's do side 1. So let's look at the side here. So how do you describe the side here? So this is the side whose x-coordinate is x and y-coordinate is 0. For 0 less than or equal to x less than or equal to 5. Right? And what's the function become? F x 0. So this is going to be some g of x now. So g of x is equal to f x 0, which is just going to be minus x. Now what about lines? Where's the max and min value of a line? There's no critical point for a line, right? Because the derivative is always non-zero for a line. Right, so the max and min values are just at the endpoints. So we have g of 0, right, so this is a linear function. I think they're all going to be linear. We'll see. Linear function, so g of 0 is 0, and then g of 5 is minus 5. All right, so I've checked this point here, and I've checked this point here. And then there's no critical point inside because it's just a linear function. So that's first side. Second side, we'll say 0y. 0y for y between 0 and 4. So g of y is going to be f of 0y. It's going to be equal to minus 3y. So just checking at the boundary, g of 0 is minus 3 is 0, and then g of 4 is minus 12. So now I've checked actually all three of these points here. So the g value here is 0, or sorry, the f value here is 0, the f value here is minus 5, and over here it's minus 12. So now I've got my third side. What's that third side going to be? How do you describe that third side? So that's the sloped side here. So x is x, and y is that? Minus 4/5 x plus 4. So this is the side x is x minus 4/5 x plus 4. And here, again, x is between 0 and 5. But actually, we've already checked those endpoints, so we don't have to worry about them again. So g of x is equal to what? It's f of x is x and y is this. Minus 4/5 x plus 4. So that function, what was that function? It's right here. So there's f of x, y. So now we're gonna write y in terms of x, like that. So this becomes x times minus 4/5 x plus 4 minus x minus 3 times minus 4/5 x plus 4. So we need to work out that function, simplify it. So this is minus 4/5 x squared plus 4x minus x plus 12/5 x minus 12. So minus 4/5 x squared. So I have 4x minus x, is 3x. So 3x, that's 15 fifths. So plus 27/5 x minus 12. So there's my single variable function. So now what do I need to do with that single variable function? To find the max and min value. We've already checked the endpoints, so all I got to do is what?
Find the critical points.
Yeah, just find the critical points. So G prime is equal to, so it's going to be minus 8/5 x plus 27 over 5. Set that equal to 0. So we've got x equal to 27 over 8. That's a crappy number. So anyway, just you know, x is 27 over 8 and put that into that function. All right, so G, so that's the only critical point. So G of 27 over 5. Now this could be a maximum point because, or 27 over 8, because right, this is a parabola that's pointed down, so that's going to be a max point rather than a min point. So what do we got here? We got minus 4/5 times 27 over 8 squared plus 27 over 5 times 27 over 8 minus 12. So, that was a terrible thing. Let us there you go. Well, yeah, of course. Haven't I steered you wrong on any of the exams yet? All right, so where was that? So, oh, I see. So from alpha, all right, minus 4/5 minus 4/5 times 27 over 8 squared plus 27/5 times 27 over 8 minus 12. So minus 2.88. Minus 2.88. It should be larger than that. What happened? It should be larger than that. So x times y minus x minus 3y. So that's minus 12 plus 12/5 x plus 3x. So 15 plus 12 is 27 over 5. But that's an upside down parabola, so that should be like a max, more of a max value. So it should be larger than the values oh, it is larger. Minus 12 and minus 5. Yeah. So the values here were minus 12 and minus 5. And that 2.88, right? So there's like a minus 12 here, minus 5, and then this is minus 2.88. So it's bigger than those two on that upside down parabola, but, you know, not bigger than the rest. So minus 2.88. Okay, fine. So after all that, what's my max value? What's my min value? Well, my min value is minus 12. What's the max? 0. Actually, this critical point didn't pan out to be either the max or the min. So max value 0, min value minus 12. Min value all right, that one is a little bit more. I would like to avoid something that's got too many boundary components like that. But anyway, that's what you get on that one. Let's try this one again. Let's say let's give a different something a little bit easier, I think, to play with. Multiple order partial derivatives. Let's take a look at the section on the chain rule. I like that one. Let's take a look at the section on the chain rule. So on exam 2, we asked one question about, or a couple questions actually, about the chain rule. This one here. I believe that was it. So number 2, what number was that? That's, here it is. Yeah, Coulomb's law, number 4 here. Coulomb's law states that the magnitude of the electrostatic force in newtons between 2 point charges is this here. Right, so force is K PQ over R squared, in which K is constant. P and Q are the magnitudes in coulombs of those 2 point charges. And R is the distance between them in meters. Okay? Supposing that P, Q, and R are functions with respect to time, T, in seconds, use the chain rule to find an expression for change in force with respect to time. So all of these, you know, F is a function with respect to time, R is a function with respect to time, P and Q are functions with respect to time, right? So all those quantities are changing. Force, the charge on P, the charge on Q, and the distance R. So those points are kind of moving through space in some way. All right. So the first thing that you want to do to notice in a problem like that, okay, and I thought that people really did quite well on that question. I was happily surprised with that. Is that F, P, and Q are all functions with respect to time. So you've got this force F, which is a function of P, Q, and R. That K is a constant. I don't know what that constant is. I don't care. It's just some constant. Okay, so F is a function of P, Q, and R. F is a function of P, Q, and R, and P, Q, and R are all functions with respect to time. So this is a standard setup for the chain rule in multivariable calculus. Right, so the chain rule says, right, that dF dt, so F ultimately is a function of t. So df dt is equal to partial f partial p dp dt plus partial f partial q dq dt plus partial f partial r dr dt, right? This standard thing here. Well, that function f, you can find the partial derivative with respect to p. It's that. You can find the partial derivative with respect to q. It's this. And you can find the partial derivative with respect to r. It's that. Oops, I think I have a minus minus. What did I do? That's supposed to be minus. That's not supposed to be a minus there. It's just minus that. Yeah, I messed that up. Okay, so, right, I mean, we had that function. Where's that function? It's right here. Right, so r is a constant. So if you want to do partial f with respect to p, partial of f with respect to p, well, r is a constant, k is a constant, q is a constant, so it's just all a constant times p. So the derivative is that constant, which is kq over r squared. The partial derivative with respect to q, everything's a constant, and then you have q. So it's kp over r squared. Partial derivative with respect to r, it's a constant times r to the negative 2. So the derivative is negative 2, this constant, r to the negative 3. Right, and that's what that answer is right there, minus 2k pq over r to the third. So now in part B in the problem, it says the following. So suppose pq and r functions, use a chain rule to find an expression for df dt. So that was part A. Part B, suppose that p is increasing 2 coulombs a second. So that's dp dt. dp dt is 0.2. dq dt is minus 0.1. Q is, or no, plus 0.1. Q is increasing at a rate of 1 coulomb a second. R is decreasing at a rate of 0.03 meters a second. So dr dt is minus 0.03. dp dt is plus 0.2. dq dt is plus 0.1. Find the rate of change of f. What is df dt when q and p are 1 and r is 0.5? So that's all the info you need, right? So except for the k, right? So p and q are 1, so that's 1, and then the r is 0.5. Q is 1, r is 0.5. P and q are 1, and then r is 0.5 to the third. This is dp dt, dq dt, dp dt, dq dt, dr dt. You just solve all that stuff and get 1.68 k newtons per second. Whatever k is. Okay, I'm not really interested in that. Then plug and chug. Right, exactly. So I was pleasantly surprised on that one. I think people like knew what they were doing there, a lot of folks. So where are those problems? So those problems are in the section on the chain rule. Here we are. The volume of a circular cylinder. So this is one like that. The pressure of a gas. I'm pretty sure I probably did this one in the lecture. 253 circular cone, frustrum of a cone, closed. 255 closed box. A closed box is in the shape of a rectangular solid with dimensions x, y, and z. Let's check out 255. So 255 in chapter 2. Or chapter 4. So this is related rates. from a Calc 3 perspective rather than the Calc 1 perspective. And you see it's got an elegance to it here. It becomes something very simple, really. It doesn't have the complications that are going on inside the Calc 1 outlook on the thing. So a closed box is a rectangular box, dimensions x, y, z. Each dimension is changing at a half an inch a minute. So it's increasing at a rate of half an inch per minute. Find the rate of change of the surface area of the box. Okay, so surface area of the box. So we got the box, right? So this is x, this is y, and then you've got some depth here, z, x, y, z. Right, and we're wondering about the surface area. All right, so dx dt is equal to dy dt is equal to dz dt is equal to 1/2 inches per minute. Find the rate of change of surface area when x is 2, y is 3, and z is 1. So find dA dt when x is 2, y is 3, z is 1. Right, so the surface area, what is the surface area of the box? In terms of x, y, z. What's the surface area of that box in terms of x, y, z?
Two xy plus two xz plus two yz.
Yeah, 2, right, exactly. So 2xy, that's for the front side, and the back side, plus 2yz, that's for the bottom and the top, right? And then for the left and the right, it's 2xz. Right, and so we have area is a function of x, y, z, and these guys are all varying with respect to time t. Right, so dA dt is equal to dA dx partial x partial t plus dA dy dA dy partial y partial t plus dA dz partial z partial t. Right, but you can find these partial derivatives. Oh my goodness, I did that wrong. Sorry. Partial a partial x. That's where the partial goes. So a is the three variables are x, y, z. So it's partial a partial x single dx dt plus partial a partial y single dy dt plus partial a partial z single dz dt. So partial a with respect to x is 2y plus 2z dx dt. Partial a with respect to y is 2x plus 2z dy dt. Partial a with respect to z is 2y plus 2x dz dt. Okay, well, we want dA dt when x is 2, y is 3, z is 1. Right? So dA dt when x is 2, 3, x, y, z is 2, 3, 1, and dx dt, dy dt, dz dt are all 1/2. So this is 6 plus 2, So this is 8 halves. This one is x and z. That's 4 plus 2 is 6. 6 halves. And then x plus y is 3, no, 5 times 2 is 10 halves. So the whole thing is equal to 4 plus 3 plus 5, 9, 12. So 12 inches cubed per minute. And that's your final answer there. Right? It's a very just elegant process now in the multivariable perspective, much different than what you get in the single variable perspective. With the single variable perspective, like you have 3 variables, x, y, and z, and you got to find, and you have this surface area thing, and then you have to have a relationship between x, y, and z, you know, which is probably the volume. But then again, you've got too many variables anyway. So it just doesn't work out as nicely from the Calc 1 perspective. It's much more limited. Here we've definitely got a, you know, a nice kind of robust, you know, widely applicable framework to go with here. All right, so as far as exam 2 goes, let's just leave it at that. Let's say chain rule, max min problems, okay? Is that fair? All right, so for chapter 4, chain rule, you know, in particular related rates, and max min problems. Unbounded domains. Is that fair? Okay. Fair and generous. Mazboot. All right, so for chapter 4, not chapter 4, sorry, for exam 4, oh, I don't have the solutions up yet. Where did I do it? Here they are. So for exam 4, you know, I mean, the repeat of all the, I mean, again, I can't ask everything. I got to leave out some stuff. But, you know, the same topics, right? Same topics. So for exam 4, all right, we have the following types of questions. So again, go back to that summary. See the summary for chapter 6. So that summary for chapter 6 that I made for you guys. Chapter 6 summary. Right, so it's all spelled out there. There's one, right, calculate a scalar line integral. Calculate a scalar line integral. 2, calculate directly a vector line integral. So calculate a scalar line integral. That calculation is always direct. The scalar line integral has no simplifying theorems, unless you can rewrite it in terms of a vector line integral. which, you might possibly be able to do, but, probably not. Okay. Calculate a scalar line integral, and that's always just going to be a direct calculation. Okay, you have to parameterize the curve C, and then plug that curve C into your scalar function and integrate from A to B. Calculate directly a vector line integral. Same sort of process. 3. Calculate a vector line integral using the fundamental theorem of calculus for line integrals. Right? That is that the line integral of the gradient of f dot dr is equal to f at, right, the end minus f at the beginning. So for gradient vector fields, for conservative vector fields. So that's, 3 type questions. 4. Calculate a vector line integral using Green's theorem. And then related to number 4, calculate a vector line integral using Stokes' theorem. Right, which was the 3-dimensional analog of Green's theorem. Right, but they're all used for calculating vector line integrals. So there's calculating a vector line integral directly, calculating a vector line integral over a conservative vector field using fundamental theorem of calculus. Green's theorem, Stokes' theorem. I'm certainly not going to ask both Green's theorem and Stokes' theorem. It'll be one or the other. Okay, because, Green's theorem is the 2-dimensional simplification of Stokes' theorem, or Stokes' theorem is a 3-dimensional generalization of Green's theorem. Right, so that's all for line integrals. So we're definitely going to have number 1. Definitely going to have number 1. No vector fields, no vector fields involved. And these are all vector field line integrals. 6. So calculate a scalar surface integral. 7. Calculate a vector flux. By the way, I watched Back to the Future 1, 2, and 3 on Netflix, only because, we've been talking about flux. I never saw them way back when. I saw the first one, but I never saw 2 and 3. And you know what? They're actually not that bad. So over Christmas break, if you want to watch something, it's, they're actually not too bad. 2 was good. The second one was really good. So calculate a vector flux surface integral directly. So not using divergence theorem. Okay, so Stokes' theorem you're going to use to calculate a line integral, so to speak. All right. So here we want to calculate a vector flux surface integral just directly. So here's a surface, parameterize the surface, calculate those partial derivatives of the surface parameterization, take that appropriate cross product, dot product with the vector field, and integrate. And then 8, calculate a vector flux surface integral using the divergence theorem. Okay, so there's essentially 8 types of questions here. Yeah, I'm not going to ask all of them. We'll say we're going to, 6 of them, say. All right, 6 of them. And again, guys, you have to do these problems in order to, be able to do them on the exam. It's a matter of practice. It's not a matter of, there's plenty of practice time. We've got a whole week, okay? There's plenty of time for you to sit down, and I hope there is. I mean, if there's not, I'm sorry to hear that, but there's should be time for you to practice this stuff. Learning math doesn't happen until you put pencil to paper. Okay? I'm guiding you as to how and when and where to put the pencil on the paper, and what to do when you put the pencil on the paper. But, actually putting the pencil on the paper and doing the work, you got to do that. I second this. What would be the real, or, all over the place, this, the line integral, the vector line integral, that is used to calculate. So you have a vector force field. So F is just some sort of force field, a magnetic force field, or a some sort of a concussive force field, some field of force, and you have a particle that's moving through that field along a path C. Right? And the work done by the field on the movement of that particle is the line integral. Right? That's how we've been talking about the dot product of two vectors. Right? Is it gives you the this notion of work. And then the scalar surface integral, well, that's again a density and mass. You have a density function, and then you calculate the mass using the line integral. And then the vector flux across a surface, so that would be used in, fluid flows across parts of a surface. The amount of a vector field that's moving across a surface in a fluid flow, or how much energy from some sort of concussive force is moving across the surface. It's all over in physics, and in engineering, some aspects of engineering. I believe in aerodynamics, it's used quite a bit. And then there's all kind of applications of statistics that I know less about. Don't worry, it's all used. But see, I'm a mathematician. I dwell on the mathematics, less so as to what the physical meaning of these things are. What about biology? Well, you got me there. This stuff, I don't know. Although differential equations does have quite a few applications in biology. Population dynamics. It's all math, guys. It's all math. Trust me. All right. So what do you want to look at now in Chapter 6? The last half hour we've got here. What should we look at? Stokes, okay. Start with that. And trust me, they never come and ask me. All my colleagues in the biology department, they never come and ask me. They're competent enough to deal with their numerical data on their own. All right. Here's my copy of the book. Stokes' theorem. So there was essentially two ways in which we used Stokes' theorem in this chapter. Let me get my list of problems that were Sign for homework. There was essentially two ways in which Stokes' theorem was applied. So Stokes' theorem is you have this closed curve C, simple closed curve C, and then with that curves as the boundary for some surface. So here was some surface S, and S is oriented from side 1 to side 2 in a way that's consistent with the right-hand rule. In other words, slide your right hand with the fingers pointing, slide your right hand along C with your fingers pointing in the direction that C is moving, and then your thumb should point you from side 1 to side 2. All right, so in this picture, the arrow S would be going this way as opposed to going that way. So side 1 is the back, and side 2 is the side that's facing us. And Stokes' theorem says that the line integral over C of f dot dr is equal to the surface integral, the curl of f dot ds. And one consequence of that, which is used in several of the homework problems, right? So a useful consequence if surface 1 and surface 2 both are bounded by C, then the two surface integrals over the curl of f are the same. So if this is surface 1 and this is surface 2, well, they're both equal to the line integral over C, right? Because the surfaces both have the same boundary, and we used that several times in a lot of the homework problems, where the homework problem said, well, the surface is this half a sphere, or the surface is this paraboloid, where the boundary is this circle. But instead, I said, okay, forget about the paraboloid, forget about the circle, let's just use the disk. Because the disk, its boundary is that circle too. Right? So you can do that. Using that flat surface as the boundary, the plane. And that can often be useful. So let's take a look at a couple problems here. So 329, 335, 344. So use Stokes' theorem to evaluate the line, well, okay, not that one. I wanted to do one where I replaced the surface. Yeah, this one. So 339. Use Stokes' theorem to evaluate the surface integral of the curl of f dot ds, where f is this. And s is the half sphere. Right, the upper half sphere oriented out towards the positive x-axis. So that's the half sphere that's going going in the x direction. Okay, I'll draw it for you. So number 339. So f is equal to e to the xy cosine z x squared z xy. All right, so, and then s is equal to this. So it's the sphere of radius 1, the half a sphere of radius 1, pointed outward. So the front half of this sphere. All right, so here's that surface. Like that. So this is x is equal to square root 1 minus y squared minus z squared. Oriented this way. Yeah. Calculate curl f dot ds using Stokes' theorem. So notice that they're not mentioning the line integral, right? Because we're not going to be using the line integral directly. We're just going to be using the fact that, you know, the curl, the surface integral of the curl is equal to the surface integral of the curl for the two different surfaces because they both have the same boundary curve. So that's what we're going to be doing. I'm going to replace, right? I'm going to replace the surface S with just the disk. So replace S with the disk D, which is just the disk of radius 1. Centered on the YZ, in the YZ plane, right? Has the same boundary curve. So D and S have the same boundary. See, same oriented boundary even, right? It's just this disk of radius 1. Or circle of radius 1, excuse me. Okay, so let's parameterize the disk. So the disk R Y Z, which is what? Well, Y is Y and Z is Z, and then what is X? What's X in this case? just 0. Exactly. Right, I mean, if you were to do it this way, you know, it would look like this. If you to do the sphere, it would be r of y z is equal to, well, y is y and z is z, and x is equal to that. 1 minus y squared minus z squared. Right, big difference. Right, big difference. I mean, here, it's just, you know, just a 0 there. And when you take that dot product, you know, having zeros around, you know, is going to be a big, you know, a big help. All right, so let's take cross product. So partial derivative of r with respect to y is 0, 1, 0. Well, that's just j. Partial derivative of r with respect to z, that's 0, 0, 1. You know, and this part is a lot simpler too. So now which cross product do I want? You know, y cross z or z cross y? For my thumb to point this way. Y cross z or z cross y? Use your right hand. Right? Curl your fingers in the direction from y to z or z to y. Which one's the right one? Y to z, yeah? Stokes' theorem. Green. Stokes' theorem says that the curl of f dot ds is the line integral over c. All right, so if this surface, S1, and this surface, S2, both have the same boundary, see? Then their surface integrals are the same, because they're both the same as the line integral. Right? Yeah, okay. And so that's the usefulness of that there. Take your right hand, okay? So the partial derivative of r with respect to y is in this direction. The partial derivative of r with respect to z is in that direction. Now take your fingers of your right hand and curl them in the direction from ry to rz. Now your thumb points in what direction? In the x-axis direction or the negative x-axis direction? So point your index fingers or curl your index fingers, right, from y to z. Now your thumb points which way? Positive x-axis or negative x-axis? Right, positive x-axis. If you take your fingers of your right hand and curl them in the direction from z to y, or z to ry, or partial of r with respect to z, partial r with respect to y, then I have to turn my, you know, you gotta, you know, throw your arm in a screwball maneuver, right? And now my thumb is pointed in the negative x-axis direction. I could never throw a screwball. It's hard, right? So it's in the negative x direction, but that's not the direction we want. We want the direction of the positive x direction, right? Because this surface, the sphere, is pointed in the positive x direction, has this boundary curve C. So we keep that direction, this boundary curve C. So we curl our fingers in that direction, and our thumb points in this direction. With our right hand, always using the right hand for the right hand rule. So ry cross rz, well, you can set it up, right? But it says j cross k, which is I, which is 1, 0, 0. Right? So now, right, we want to calculate this surface integral of the curl. Surface integral of the curl. So let's calculate the curl first of all. So here's f. So now the curl of f is equal to what? Well, it's I, J, K, e to the x, y, cosine z, x squared z, x, y. Whoops, I forgot the differential operator, the gradient operator. Partial x, partial y, partial z. All right. Now, by the way, when I calculate the integral, I'm going to be taking the dot product with ry cross rz. So all I care about is this component, right? The component in the x component. So in the x component, it's going to be 2xz. Oops, that's wrong. In the x component, it's going to be x minus x squared. All right, partial derivative of this with respect to y is x. Partial derivative of this with respect to z is x squared. And then here, I don't care. I don't care what they are. So this is x squared. All right, so the surface integral of the curl of f ds is equal to, by Stokes' theorem, so this was the sphere, the surface integral over the disk of the curl of f dot ds. I guess let's put dd for kicks. Right, so this is the double integral over r, right, where r is the domain for the disk, right? I guess we never wrote that down. Where is that? Right, so for y and z, for y squared plus z squared less than or equal to 1. So on that disk of radius 1. So it's the double integral over r of the curl of f, which is this, right? X minus x squared, right? But what is that? Right? The curl of f over r y z dot ry cross rz dA. But what's the curl of f over ryz? So y is y. Remember ryz was what? ryz, right, was y is y, z is z, and x was 0. So what is this? It's just 0 something in the other coordinates. Right, the x minus x squared is 0. Other coordinates I don't care. So it's double integral over r, 0, don't care, dot this, but this was 1, 0, 0. dA. This dot product is just 0. Now, if you were to use the half sphere to do that calculation, no, it would not come out that easy. You would actually like go through some pain to try to calculate that. Okay, there would definitely be some details that would need to be worked out. Right. So under that vector field, it doesn't flow across that disk at all. The net flow across that disk is 0. All right. So that's one way in which Stokes' theorem was used. The other way in which Stokes' theorem is used is just to calculate the line integral over C. So there should be a few problems that are stated in that fashion. 344, 346. Use Stokes' theorem. Yeah, so like 347. Uses Stokes' theorem to calculate for the vector field this, where S is this, or no, it's not stated that way. Where is it? S is the hemisphere. They shouldn't give you the surface. They should just give you the... (351, 353, 356). Yeah, why not? Disk or the plane or something of that sort. Yeah, so like 357 is stated in this fashion. So F is equal to this here. So number 357. So F is equal to XY, 2Z, 2Y. Like that. And C is the intersection of the plane x plus z equals 5 and x squared plus y squared equals 9. I think that's what it said, right? Yeah, x plus z equals 5 and x squared plus y squared equals 9. So you've got this cylinder. And then you've got this plane that's passing through like that, and it's intersecting the cylinder in this oval shape. And we'll say they didn't say it in the problem, but oriented counterclockwise when viewed from above. So calculate, right, the line integral over C of f dot dr. Right, so here, using Stokes' theorem. Right, using Stokes' theorem. So I should label these x squared plus y squared equals 9. So by Stokes' theorem, the line integral over C of f dot dr is equal to the surface integral of the curl of f dot ds, where S is the surface that's going to have C as its boundary. So what surface would you pick? What surface would you pick?
X squared plus y squared equals 9.
Well, that doesn't have C as the boundary. It has C on its boundary. Well, sorry, C lives within the surface. Right? You would actually pick the plane. Oops. The plane in here, directed that way. That bit of the plane, that oval bit of the plane, has as its boundary C. Right? So pick S to be x plus z equal to 5 inside the cylinder. So the cylinder gives you the boundary. Right, so this is r of x, y, where x is x, y is y, and z is 5 minus x. For x and y where? Which x's and y's? Here's r down here in the xy plane. What is that? right? That's all x squared plus y squared. That's all x squared plus y squared less than or equal to 9, the disk of radius 9. So the surface is just the plane. The function of the cylinder there, the purpose of the cylinder, is to give you that little bit in the xy plane that's going to be the domain for that surface. So it's the part of the plane above this circle. Right? I mean, if you were to project this surface down into the xy plane, then you get exactly that circle. If you shine the light straight down the cylinder, the shadow you get in the xy plane is just the inside of that cylinder. All right, so you calculate the curl. I, j, k, partial with respect to x, with respect to y, with respect to z. And what was it? xy, 2z minus 2y. So this is equal to minus 2 plus 2. No. Minus 2 minus 2. J is 0 minus 0. And the k is 0 minus x. Right, so it's just that, the curl of f. So the line integral over c is equal to, via Stokes' theorem, the surface integral of the curl of f dot ds. So that's the surface integral of this vector field minus 4, 0 minus x dot ds. So this is equal to the double integral over r of curl of f over rxy dot, oh, I didn't do the rx cross ry. So here rx is equal to 1, 0, minus 1. ry is equal to 0, 1, 0. So rx cross ry, so this is equal to I minus k cross j. So this is I cross j minus k cross j. So this is k. And then k cross j is minus I. So that's minus 1, 0, 1. Check that real quick. So in the x, you have 0 plus 1. Oops. I cross j is k minus k cross j is negative I. That's positive I. So 1, 0, 1. Dot 1, 0, 1 dot dA. Not dot, sorry, dA. So this is equal to the double integral over r. Curl of f, that's just this. X is x, y is y, and z is whatever it was, but there's no z's. Dot 1, 0, 1 dA. So this is minus double integral over r, 4 plus x dA. And then you have to put this into polar coordinates. So r goes from 0 to 3, theta goes from 0 to 2 pi. This is 4 plus r cosine theta, r dr d theta, which is equal to something. Okay, so and we had to change it. We had to change it to polar coordinates because r was that circle of radius 3. So 0 is r3, and 0 is for 0 theta from 0 to 2 pi. right? Because we can't really express it easily in terms of Cartesian coordinates. Okay, so that's two different applications, two different ways in which you can apply Stokes' theorem.
So the equation of the plane got you the intersection, but you also needed the equation of the circle for your region to integrate
The
over.
circle is the region for x and y. The plane is just the surface that you're using. Right, the intersection of the plane with the cylinder is that boundary curve, see? But what surface has that boundary curve? The plane, the part of the plane that's inside the cylinder. So yeah, I think what you said was right. The way you said it was good. But we never figured out what that boundary curve is. We never parameterized the boundary curve, right? Because all we needed to do was parameterize the plane instead. Okay, so so we'll go through the material for chapter 4 again, or exam 4, chapter 6 here. Okay, again, there's 8 types of questions that I'm going to ask, probably 6 of them, right? And then a couple questions from chapter 2. Chain rule, max min, and that's it. Wednesday, and nothing. Yeah, no common final. There's no common final for Calc 3. Okay, it's just us. This class section. So it was. I wrote it down here. It's final exam is the 9th, 5:45. Not at 6, guys. Don't come at 6. 5:45. 5:45 to 7:45. Okay, don't come at 6:10, please. 5:45 to 7:45. So we'll start at 5:45 sharp. So come here a few minutes early. All right. Okay. So I'll see you guys next week. Email me with any questions. Okay. Questions or concerns. All right. So do the reviewing, and I'm sure everyone's going to be fine.